Hello everyone, welcome to our YouTube channel Electronics Maddie. In this video, we're going to see the simulation of an 18 pulse control rectifier in Matlab. This is the circuit diagram of an 18 pulse control rectifier. It can be built by having a combination of three 6 pulse control rectifier, that is three thyristor bridges, 6 pulse thyristor bridges in this particular fashion. So these are zigzag transformers which is used to provide the required phase shift with respect to the supply terminals and the thyristor bridge. So we will be constructing the circuit. So I did get a lot of requests with respect to the 12 pulse control rectifier video that I made. So people wanted to know how 24 pulse control rectifier can be built, 36 can be built. So just want to go step by step. Let us simulate 18 pulse control rectifier in this video, and in my upcoming videos I'll be showing how to simulate the rest of them as well. So all right, so once the circuit diagram is taken a look upon, we will get started. We'll get into our simulation in Matlab. So all right, here we are. So this is the Simulink library browser. So we'll be searching for the components that are required. At the first place, we will be requiring a three-phase AC source. So supply, this is used as a supply. So search for it in this particular fashion and add this block. Once this is added, we will be requiring a VI measurement block. So search for VI measurement and add this block to our model. We will be requiring a PLL synchronization block. So search for PLL and you'll be getting it right at the bottom. Scroll a little down and choose the one that is there in three phase. So be very careful while selecting this. So add this block as well. So once all of these are added, we will be requiring a transformer, which is basically a zigzag transformer used in this case. So scroll a little down, it will be there over here. So add this block as well. Once this is done, we will be requiring a pulse generator block. So search for pulse. You will be getting it in the search results over here right at the bottom. Scroll a little down, it will be right underneath. So over here you see the one that is there in 6 pulse and 12 pulse. Since we are using three 6 pulse converters, universal bridges, so we will be choosing the ones that is there in 6 pulse. So once this is also added, we will be requiring a thyristor bridge, isn't it? So which is basically the heart of our circuit. So search for thyristor, scroll a little down, choose the one that is there with respect to 6 pulse. So add that block as well. So once okay, I've added the pulse generator block again. So this is not necessary. We've already added them in the previous case. So add the one, this is the universal bridge that we are supposed to add. So add universal bridge. So once this is done, we will be requiring a series RLC circuit, which is basically converted to a resistor or an inductor or a capacitor based on the type of element that is required. So search for it and add it. And we need to measure the voltage and current. So we will be searching for voltage measurement block and add this block as well. Once this is done, we will be requiring to determine the RMS value. So search for mean, that is how we will be able to get the RMS values. That's the reason. So choose the ones that are there in black with respect to power electronics. The ones that are there in blue are used for a different purpose. So we will be adding this block. And once this is done, be very careful. We are not supposed to use this RMS block that is used for digital signal processing, and this is used for power electronic applications in order to determine the RMS value. We will be requiring a display in order to see how the waveform looks like. So search for display, and you will be getting it right over here. We'll also require a scope, so add the scope over here as well. So once we have added all the components, we will be placing them in appropriate positions so that we can get started off with our circuit connections. So we have two blocks over here. So we'll copy paste them later on based on our requirement. A source should be in the left hand side. So I'm just placing them in appropriate positions so that we can get started. So a zigzag transformer is to be used before the universal bridge for phase shifting purposes, and a synchronization block at this particular position. So once all of these are done, now we can get started with our circuit connections and copy pasting various values. So first step, we will be giving the three sources to the VI measurement block, and we will be double clicking on it and change this to current measurement to no, because we only want the voltage measurement and we'll be giving it to this. So we will be giving it to the PLL synchronization block. The purpose of PLL synchronization block is to synchronize with respect to our supply frequency. So that's the reason why we'll be using it. Choose the omega t terminal, and give it omega t with respect to the pulse generator block. And once this is done, we will be requiring three zigzag transformers. So copy paste three zigzag transformers in this particular fashion. I'll be zooming out the circuit a little bit so that we can see the entire circuit. I'll be placing this in an appropriate position in this particular fashion. And once this is done, we will be requiring three universal bridges, Control C, Control V. So I'll be placing them right adjacent to these blocks in such a way that we can connect them easily. So once all of these are done, first step is to short these terminals with respect to minuses ABC. This is according to the configuration in which the zigzag transformer is to be connected for simulating them in 18 pulse mode. And we will be connecting the respective phases, that is with respect to A, B, C, to the respective terminals over here, which is basically connected to the supply. And we will be doing the same with respect to the other phases as well. So we'll be connecting A phase with respect to A, B to B, and C to C. So this is done for all the three transformers because eventually we will be using the same supply, which is a three-phase source here. So once all of these are done, we will be giving them in turn to these thyristor bridges, zigzag transformers output. So we will be following it for the other two configurations as well in this particular fashion. So do connect in this particular way. And once this is also done, our next step will be to connect this to enclose them in form of a circuit, and then we can connect the load between these positive and negative terminals. So once all of these are done, so now we can click on this and we will change the pulse width to 120 degree over here. The reason is very simple. Be very careful. We are using 18 pulses, so each bridge should be conducting for a period of 120 degrees. So pulse width with respect to 360, 360 divided by 3, three bridges are there, 120 over here. But the triggering will be different. Okay, I have to use a constant block in order to trigger the firing angle. So search for constant, that was not added previously. So search for constant over here. You will be getting it right at the top. Add this block as well. So this is the one that is used in order to fire the thyristor. Over here, what value you will give is what is the firing angle. I'll be choosing 10 degrees. I'll be triggering it for 10 degrees with respect to this circuit, and I will be giving it to the gate terminals for the first universal bridge. So similarly, we can follow the same pattern with respect to the bridges, the other two bridges as well. So Control C, Control V. So copy paste this. I'll be placing it in this particular position so that we can clearly see it. So synchronization, anyways, it is the same. I think one block is more than enough. If you copy paste it again, you will be connecting it to the same terminal, isn't it? So that's the reason why one block is enough, because all of them should be synchronized to the same supply frequency. And I'll be connecting the pulse terminal to the respective pulse generator block over here, gate terminals with respect to the universal bridge. We'll be requiring the pulse that is 10 degree. Again, I'll be connecting it to 10 degree respectively in these two cases over here. So we have connected with respect to the firing angle and all those things. Once this is done, we will be requiring an inductor just to make sure the value of the inductor. So I am not going on with an accurate design with respect to it. So I'm not showing the design steps for that. So it depends totally on your application and the way you want it to be designed. So I'm choosing the values of LNC by trial and error method. So based on the amount of current and how to, just like this is video made to understand how it can be simulated, and so that we will be able to see the output waveform clearly. And based on that, I've chosen the values. So it's based on trial and error, but there are accurate designs available in various textbooks. Please do refer to it. We will be connecting a load resistor at this particular terminal. The reason why I'm using a capacitor is to reduce the amount of ripple that is there at the output. Inductor is to study the output current so that we can see if we want to measure how the output current looks like. And once this is done, we will be using a resistor, and its value is chosen to be 1400 ohms. So the value of resistor chosen is very high. People might ask me a question as why is this very high? So in experimental like if you are performing this in experiment in laboratory, if you are trying to rig up the circuit, you will basically have a rheostat in your laboratory, and basically it will be having the range of about 3000 ohms or 1500 ohms, and you'll be moving the slider from 0 to 1400. So that's the reason that was there in my thought process before using 1400 ohms. So I will be connecting this as the load at this particular point, and once this is done, a voltmeter is to be connected at this particular terminal with respect to it. And one of the most important steps is to change the fundamental frequency. A lot of people make this mistake. If it is chosen to be 60 hertz, you will be getting wrong answers at some cases, not in all the cases. So it's preferable if you choose it to be 50 hertz if you're doing it for 50 hertz. If you're doing it for 60 hertz, which is used in various other countries, then do it for 60 hertz. No problem at all. And I'll be connecting the voltmeter at the scope over here. Once all of these are done, we have rigged up a circuit, but we need to enter the parameters according to our circuit. So phase-to-phase voltage is 254.0305 volts. It's very simple, 440 divided by root 3. Do that, you will be getting this value. And the frequency is 50 hertz with respect to our supply. Click on OK. And once this is done, we will be entering the parameters of the zigzag transformer. So it is given to be equal to 100 into 10 power minus 6, 10 power plus 6, sorry. So I will not be choosing a very high value as such. I'll be choosing 50 into 10 power 3, and frequency I'll be changing it to 50 hertz. So based on this, the nominal power, you will be getting an output at the with respect to the output terminals. So I'll be copy pasting the same values with respect to the other two zigzag transformers as well, so that they are in synchronism with respect to each other. So we have entered all the parameters with respect to our circuit, I believe. So we can simulate them and look at how the waveform looks like. So I am not going to give a huge simulation time. I'm going to give it in zero point 0.5 or zero point 0.3, not more than 1 or 1.5, because synchronization, this block takes a lot of time to simulate according to our supply frequency. So that's the reason. So now I'll be clicking on run. All right, so one of the most important steps that I have not included is the power give block, which is the heart of our circuit. So add that block as well. At times you might get these errors as well. So be very careful, add this block. This is responsible for the simulation to take place with respect to the circuit. So now we'll be clicking on run. All right, now we'll check the waveform as how it looks like by double clicking on the scope. So over here, if you increase the simulation time, it will take a lot of time as well. So you can see these are the pulses that are produced, which is almost sinusoidal in nature. If you restore it to the original view, you will be getting it in a very small functionality, like you will see it in very small scale. And now in case you want to measure the source current as such and compare it, you can use an ammeter at the source terminals. We'll go into the Simulink library browser and search for current measurement block. You will be getting it right at this particular point. So add this block as well. So we can check how the supply voltage is there as well. So if in case you want to see with respect to the input terminals, we can do that. So I am connecting this to this point and the supply current at this point. Additionally, as I told you, in case you want to see how the phase voltage looks like, so I can connect this between phase A and B, and I can connect it to the third point. And now we'll again click on run and see how the waveform looks like. All right, let's double click on the scope to see how the waveform looks like. We'll be categorically dividing them into three different sections so that we can see them clearly. So over here, it looks like the current is very less and it is going in negative and positive directions. So we can increase the nature of the current based on our requirement. And if you want to check how the load current looks as well, you can definitely do that. If you carefully observe with respect to one complete cycle with respect to the source, there are small pulses that are produced, and which is almost the ripples is also very less. And further, when you see it in the original view, it looks very small, and the current is also oscillating in nature. So you can see these are the pulses that are generated, and which is much better than in comparison with our previous circuit, that is with respect to 12 pulse control rectifier. So furthermore, we can do this analysis for for 24 pulse, 36 pulse as well. So which will be done in my upcoming videos. Please do watch out that. So this is how we'll be simulating 18 pulse control rectifier in MATLAB. In case you have any questions, feel free to reach out by typing in your questions in the comment section below. Thanks for watching this video. Please do keep supporting. Thank you.